Today we are going to discuss about Bethe equation. Here we have considered the multi-layer adsorption. So in the case of multi-layer adsorption, we cannot apply the Langmuir adsorption isotherm. It is applicable only for monolayer adsorption. So in 1938, Stephen Brenner, Edward Teller and Paul Emmelt combinedly suggested the Bethe equation in order to explain the multi-layer adsorption. The basic assumptions in deriving Bethe equation are: first one, there exists multi-layer adsorption. The existence of multi-layer adsorption is due to the van der Waals force of interaction. The second one is that adsorbent surface is flat and uniform so that it makes easier the multi-layer adsorption. And there is no lateral interaction between the adsorbate molecules, and for each layer we can apply the Langmuir adsorption isotherm for deriving the Bethe equation. And in each layer, for the adsorption, the energy of adsorption, that is heat of adsorption, EAD, is equal to heat of liquefaction, that is liquefaction energy, and this is applicable, this equality is applicable for all layer except for first layer. ഫസ്റ്റ് ലെയറിൽ മാത്രമാണ് ഹീറ്റ് ഓഫ് അഡ്സോർപ്ഷൻ ഡിഫറൻസ് വരുന്നത്. ബാക്കി എല്ലാ ലെയേഴ്സിലും അത് ഹീറ്റ് ഓഫ് ലിക്വിഫാക്ഷന് ഈക്വൽ ആയിരിക്കും. ആൻഡ് ദീസ് ആർ ദ ബേസിക് അസംഷൻസ് ഇൻ ഡിറൈവിംഗ് Bethe equation. Let us start the derivation. First of all, let SI be the surface area per layer. ഓരോ ലെയറിൻ്റെയും സർഫസ് ഏരിയ നമ്മൾ SI എന്ന് വെച്ചിട്ട് ഡിനോട്ട് ചെയ്യുകയാണെങ്കിൽ total surface area A equal to S0 for the 0th layer plus S1 for first layer plus S2 for second layer and so on. So A equal to sigma I equal to 0 to infinity SI. അതായത് ഒന്നും അഡ്സോർബ് ചെയ്യുന്നതിന് മുന്നേ അഡ്സോർബൻറ്റ് സർഫസിനെയാണ് 0th ലെയർ എന്ന് പറയുന്നത്. അതിനുശേഷം ഫസ്റ്റ് ലെയർ വന്നു കഴിഞ്ഞാൽ അത് S1 ആയി, then S2 and so on. Similarly, if V0 is the volume of adsorbed gas per unit surface area, അങ്ങനെയാണെങ്കിൽ ഓരോ ലെയറിൻ്റെയും വോളിയം നമ്മൾ ആഡ് ചെയ്ത് കഴിഞ്ഞാൽ നമുക്ക് എന്ത് കിട്ടും? ടോട്ടൽ വോളിയം കിട്ടും. Therefore, the total volume V is equal to 0 into S0 into V0. This is the total volume for the 0th layer. Plus 1 into S1 into V0 is volume for first layer plus etc. And this can be reduced to V0 into sigma I equal to 0 to infinity ISI. Here 0, 1, 2 എന്ന് നമ്മൾ കൊടുത്തിരിക്കുന്നത് ഈ ഒരു ഫോമിലേക്ക് ആ എക്സ്പ്രഷൻ മാറ്റാനും മാത്തമാറ്റിക്സ് കുറച്ചും കൂടി ഈസി ആക്കാനാണ്. പിന്നെ അതിൻ്റെ ഒരു സിഗ്നിഫിക്കൻസ് എന്ന് പറഞ്ഞാൽ ഇത്രയേ ഉള്ളൂ. നമ്മൾ 0th ലെയറിലൊന്നും നടന്നിട്ടില്ല, പിന്നെ ഒരു ഫസ്റ്റ് ലെയറാണ് കണക്കാക്കുന്നത്, സെക്കൻഡ് ലെയർ ആണെന്ന് ഐഡൻറ്റിഫൈ ചെയ്യാൻ വേണ്ടിയിട്ടാണ് ആ 0, 1, 2, 3 എന്ന് നമ്മൾ കൊടുത്തിരിക്കുന്നത്. Now we are dividing V by A, that is total volume by total area, equal to V0 into sigma I equal to 0 to infinity ISI by sigma I equal to 0 to infinity SI. ഇത് V0 ഇപ്പുറത്തെ ഭാഗത്തേക്ക് കൊണ്ടുവരുമ്പോൾ നമുക്ക് എന്ത് കിട്ടും? V by A V0 equal to sigma I equal to 0 to infinity ISI by sigma I equal to 0 to infinity SI. And this is equal to V by Vm because A into V0 equal to the total volume Vm. Next, we can apply equilibrium condition for each set of layers. First, consider 0th and first layer. Here, according to Bethe equation, we can apply the equilibrium condition as rate of adsorption on the 0th layer will be equal to rate of evaporation from the first layer. Now we can derive equations for rate of adsorption on zeroth layer and rate of evaporation from first layer, and then we have to equate both of them. Here the rate of adsorption is proportional to the pressure and surface area available, that is S0. Therefore rate of adsorption is equal to some constant K1 into P into S0. Rate of evaporation is proportional to the surface area available, that is S1, and also the adsorption energy, that is E raised to minus E1 by RT, which is equal to K inverse S1 E raised to E1 by RT. At equilibrium, K1 into P into S0 will be equal to K inverse into S1 into E raised to minus E1 by RT. So from this, S1 equal to K1 by K inverse into P into E raised to E1 by RT into S0, and this is equal to Y into S0 because the constants are equated as Y, and Y is equal to K1 by K inverse into P into E raised to E1 by RT. Now we can repeat the same procedure for equilibrium between first and second layer. Here, like the previous case, rate of adsorption will be equal to K2 into S1 into P. Rate of evaporation will be K inverse 2 into S2 into E raised to minus E2 by RT. At equilibrium, we can equate both of this equation and we will get S2 equal to K2 by K inverse 2 into P into E raised to E2 by RT into S1. And similarly, we can apply this equilibrium condition in each pair of layers, and we could obtain general expression SI is equal to Ki by K inverse I into P into E raised to EI by RT into S I minus 1. Now, from the assumptions of wet equation, we says that E2 equal to E3 and etc. equal to EL. അതായത് ഫസ്റ്റ് ലെയർ ഒഴികെ ബാക്കി എല്ലാ ലെയറിനും എനർജി ഓഫ് അഡ്സോർപ്ഷൻ എന്ന് പറയുന്നത് എന്താണ്? എനർജി ഓഫ് ലിക്വിഫാക്ഷൻ ആണെന്ന് നമ്മൾ പറഞ്ഞിരുന്നു. സോ ഈ S2 മുതൽ നമ്മൾ E2, E3, E4 എന്നുള്ളത് മാറ്റിയിട്ട് EL ഹീറ്റ് ഓഫ് ലിക്വിഫാക്ഷൻ ആക്കുകയാണ്. ആൻഡ് ദെൻ എഗെയിൻ K ഇൻവേഴ്സ് ബൈ K എന്നുള്ള കോൺസ്റ്റൻറ്റിനെ നമ്മൾ G എന്ന് വിളിക്കുകയാണ്. Now we get the general expression SI equal to Ki by K inverse into P into E raised to EI by RT into S I minus 1. So we can write S2 as K2 by K inverse 2 into P into E raised to E2 by RT into S1. Here K2 by K inverse can be replaced by 1 by G. Then E2 can be replaced by EL. So all these constant can be taken as X. That is X is equal to 1 by G P into E raised to EL by RT. So we get S2 as X into S1. The previous case we could get S1 equal to YS0. അത് നമുക്ക് മുന്നേ കിട്ടിയതാണ്. S1നെ നമ്മൾ Y into S0 എന്ന് എഴുതിയിരുന്നു. Therefore S2 is equal to XYS0. Similarly, S3 can be derived in the same manner and we could obtain S3 is equal to X square Y S0. So we can generalize the expression for SI as X raised to I minus 1 into Y into S0. So SI equal to X raised to I minus 1 into Y into S0. This can be again written as X raised to I by X, which is X raised to I minus 1 into Y into S0. And this is equal to X raised to I into C into S0, where C equal to Y by X. Next, we can rewrite the expression V by Vm is equal to sigma I equal to 0 to infinity I x Si divided by sigma I equal to 0 to infinity Si. ഇനി നമുക്ക് Si എന്നുള്ളതിന് സബ്സ്റ്റിറ്റ്യൂഷൻ കൊടുക്കാം. Therefore we will get V by Vm is equal to sigma I equal to 0 to infinity I into x raised to I into C into S0 divided by sigma I equal to 0 to infinity Si can be split into two terms as S0 plus sigma I equal to 1 to infinity Si. Again, C and S0 in the numerator are constant. We can take them outside. So S0 C into sigma I equal to 0 to infinity I x raised to I can be written in the same manner as sigma I equal to 1 to infinity I x raised to I. അതായത് I equal to 0 to infinity എന്ന് എഴുതിയാലും equal to 1 to infinity എന്ന് എഴുതിയാലും സെയിം ആണ്. കാരണം സമ്മേഷൻ ആണ് വരുന്നത്. I0 ആകുമ്പോൾ പിന്നെ എന്തായാലും അത് പോകും. അപ്പോൾ 0ൻ്റെ കേസ് നമുക്ക് അവിടെ കൺസിഡർ ചെയ്യേണ്ട ആവശ്യമില്ല. അതുകൊണ്ടാണ് I equal to 0 to infinity എന്നുള്ള സമ്മേഷൻ നമ്മൾ അടുത്ത സ്റ്റെപ്പിൽ 1 to infinity എന്നാക്കിയത്. കാരണം ഡിനോമിനേറ്ററിലും നമുക്ക് സിമിലർ ടേം ആണ് വരുന്നത്. ആൻഡ് ഇൻ ദ ഡിനോമിനേറ്റർ S0 plus sigma I equal to 1 to infinity x raised to I C into S0. And from denominator we can take S0 as a common factor. So we can cancel the S0 term from numerator and denominator. So we get V by Vm is equal to C into sigma I equal to 1 to infinity I x raised to I divided by 1 plus C into sigma I equal to 1 to infinity x raised to I. In maths, we can write sigma I equal to 1 to infinity I into x raised to I as x by 1 minus x whole square. And sigma I equal to 1 to infinity x raised to I can be written as x by 1 minus x. So we can put this substitution in the above equation for V by Vm. We get V by Vm as C into x by 1 minus x whole square whole divided by 1 plus Cx by 1 minus x. Now we can simplify this. Taking LCM in the denominator, we get V by Vm is equal to Cx by 1 minus x whole square whole divided by 1 minus x plus Cx by 1 minus x. So we can cut the 1 minus x term in the denominators. So after simplification, we get V by Vm equal to Cx by 1 plus C minus x. ഒരു ടേമും കൂടെ വരും, 1 by x കൂടെ ഡിനോമിനേറ്ററിൽ വരും. Therefore V by Vm equal to Cx by 1 plus C minus 1 into x into 1 minus x. Now we can cross multiply the equation and simplify. Now we get, after cross multiplication, V into 1 minus x by x equal to CVm by 1 plus C minus 1 into x. Taking reciprocal, we will get x by V into 1 minus x equal to 1 plus C minus 1 into x by CVm. We can separate the right hand side. Then 1 by CVm plus C minus 1 by CVm into x. Now we can plot the graph. If we plot a graph between x by 1 minus x into v versus x, we will get a straight line with a y-intercept equal to 1 by CVm and slope is equal to c minus 1 by CVm. Now just do the equation 1 by slope plus intercept. So which is equal to 1 by slope means 1 c minus 1 by CVm, intercept is 1 by CVm, and this can be reduced to 1 by c by CVm. We can cancel c and we will get 1 by slope plus intercept equal to Vm, and from this Vm can be calculated and this Vm can be used to calculate the surface area. So, in order to calculate surface area by Bett equation, we can get the value of Vm as 1 by slope plus intercept, and this can be used to calculate the surface area. Today we are going to discuss an expression for surface area calculation. We can calculate surface area either in terms of Langmuir-Adsorption isotherm or in terms of Bett equation. That is, in the expression for surface area, we have to substitute the value of Vm, and the value of Vm can be either obtained from Langmuir-Adsorption isotherm or from the Bett equation. Now we can derive an expression for surface area calculation. From the derivation of adsorption isotherm, we have seen that theta is equal to some constant Kp by 1 plus Kp, and this can be equated in terms of volume as V by Vm, where V is the volume of adsorbed gas molecules and Vm is the volume required to complete a monolayer adsorption. That is, it is the maximum volume available for adsorption. So, V by Vm is equal to Kp by 1 plus Kp. Now, surface area equal to N into Na into S. Here N is the number of moles, Na is the Avogadro number, and S is the surface area of a single gas molecule. So, N into Na gives the total number of molecules. And we assume that the ideal behavior, so we can substitute for N. We get P0 Vm by R T0 into Na into S. Here 0 subscript indicate under STP condition. So under STP we can reduce the P0 by R T0 by putting the molar volume condition. And this is equal to, surface area will be equal to Vm into Na into S by 22.414. So if we know the surface area for a single gas molecule and we have the Avogadro's constant, we can calculate the surface area if we are getting the value of Vm. And the value of Vm can be obtained either from Langmuir-Adsorption isotherm or from the Bett equation. Their graphical representation will give the value of Vm. According to Langmuir-Adsorption isotherm, V by Vm equal to Kp by 1 plus Kp. We can cross multiply this equation, and on simplification we will get an equation like 1 by V is equal to 1 by Vm into 1 plus 1 by Kp. Then now we can plot a graph, and from this graph the intercept, y-intercept is 1 by Vm, and from this Vm can be calculated, and this again can be used to calculate the surface area. Second method is by using Bett equation. From the Bett equation, the graphic representation give an intercept 1 by Cvm and slope as C minus 1 by Cvm. So, from this Vm can be calculated by the equation Vm is equal to 1 by slope plus intercept. Either of this expression can be used to calculate Vm and thereby the surface area of an adsorbent.